David Smith here with yet one more flipped classroom math lesson. 3 tips before we start. First, you can adjust the playback speed to suit you. You can also pause a video at any point and jot down notes or write down questions for our next class. Lastly, you can turn on the captions and read my words on the screen. Today's topic, is there really a difference? Unit review. So we're going to go through all the things that we did in this chapter in our book and mention all of them. What I'm not doing here is detailed problems in each subject area. For that, you have your old homeworks, you have the keys that I've published in our Google Classroom, and you have each other to troubleshoot and help and support each other. So you still need to dig in and review the math, but this will be a guideline to what kinds of things to work on. Okay? So first off, here are the things we're going to talk about in this video. We started off by talking about samples and populations and how to do that well. We did a few frequency diagrams along the way, and we used those a little bit later with coins. We did a bunch of different problems with coins and dice, so you need to be familiar with those. We moved on to working out how to formulate hypotheses and null hypotheses, and we did that 2 ways. We had a user-friendly hypothesis, and then we used the special language that we developed in class for that. We took a little side trip talking about standard deviation and normal distribution, and we used that to answer some questions. People found this challenging, so make sure that you review that. Then, in preparation for doing a good chi-square analysis with populations, we talked about finding expected values. And it's easy to do that with coins and dice, a little harder to do that with people. But the math is pretty simple, you just have to remember how to do it. We also did chi-square calculation. So this is how to actually do that formula to come up with your chi-square value. And then we accepted or rejected our null hypothesis. This was kind of in our conclusion zone. We talked about how to use the correct modifier, like hypothesis is more likely true, most likely true, very likely true, things like that. And in this zone here, we talked about the chi-square probability table and how to use that to either accept or reject the null and formulate a good conclusion. So we're going to talk about all of these things briefly in this video, so let's get started. Okay, here's the key concept for this. The sample must represent the population that we're studying. So typically with a statistical study, we pick a small sample, we analyze that, and then we generalize our results to a wider population. So for example, let's say we want to learn more about the habits of people with respect to smoking, like those who don't, those who do, kind of what our percentages are for that. Okay, so if we want to learn about that, the habits of the whole population with respect to smoking, we need to pick a sample population that represents the whole. So here's a bad example. What if I go to a smoking cessation workshop? This is a place where people would go to learn and get support for how to quit smoking, because we all know it's a bad habit. So we go to that workshop and we interview people and all that kind of stuff. Now that's a bad sample, because if you remember from the beginning here, I said we want to learn about the whole population's attitudes about smoking. So the non-smokers are also important. Their feedback and their responses to our questions, it's important because we want to know about the whole population. If I go to a smoking workshop, I'm only interviewing smokers. So my opinions, what I learned from that will be valid, but it will only be valid for smokers. And if my study wants to talk about the whole population, I need to include non-smokers as well. Okay? So a good sample for this study might be a random sample that pulls out all kinds of people from your city or your town, but doesn't select smokers only. Okay, one of the central themes in this chapter was dealing with situations involving coins and dice. And I think you guys pretty much know the probabilities involved with coins and dice, and we did explore those in our probability chapter several months back. But we are standing on some of that knowledge. Fortunately, it's fairly simple. So coins, there's only 2 possible outcomes, heads or tails. And that means there's a 50% chance of either one. We're assuming that each outcome is equally likely. In fact, for theoretical probability, that assumption is the correct one. However, if you think you have a rigged coin, then you might not be able to assume that. Dice, there are 6 sides on a die, 1, 2, 3, 4, 5, 6. So each one has a 1/6 chance of coming up. So if you roll a die 1 time, you have a 1/6 chance of rolling something like a 5. Now we used coins and dice throughout this chapter to analyze situations. So we used that to build the key concepts. We calculated some chi-squares with coins and dice, and so on. Okay, we spent a little time building frequency diagrams, and that came in a little later to show the normal distribution with coin flips. But right now, I just want to show you how to make a frequency diagram. So this situation involves a die. We're rolling a die, and then we're recording what we got. So that's here, rolls. So that means just first roll was a 6, second roll was a 5, next I got a 3, got another 3, and so on. So this is a hypothetical session where I rolled a die a bunch of times. So to put that in a frequency diagram, what we need to do is it's basically a bar graph, right? So on the horizontal axis, that's the number of trials for each one. So I have a space for 1s, space for 2s, 3s, and so on all the way to 6. The vertical, the y-axis, has the frequency, which is the number of times we got that result. So let's populate this diagram. I'm going to start with the 1s. How many 1s did I get? I got 1, 2, 3 1s. So that would be 1, 2, 3. So that's my bar for 1s. How many 2s did I get? 1, 2. I got 3 2s as well. So there's my 3 2s. How many 3s did I get? Looks like I got 1, 2, 3 3s. How many 4s? Looks like I got 2 4s. So that would be, this bar would be a little shorter. Like that. How many 5s? I got 1, 2, I got 3 5s, so we're back up here. And then how many 6s did I get? I got 1, 2, 3 6s. So that's a pretty even distribution, and that shows you that when I just randomly, quote unquote randomly, generate all these numbers, I actually made them pretty even. That's a natural thing that humans do. We tend to assume that if I rolled a die that many times, it would come out pretty evenly. But you know from experience that it might not. We might have gotten 5 3s, and we might have only gotten 1 4. That's very possible for this many rolls. But regardless, that's how you make a frequency diagram. Okay, we spent quite a bit of time formulating hypotheses and null hypotheses. And this was a little challenging. It took us a couple weeks until everybody felt really comfortable using the special language. So I'm going to start with the user-friendly version, and I'm going to have you pause the video and write the special language version of this hypothesis. So I'm a student, and I just do my data snooping, right? I'm just watching what people are saying around me, and I get this feeling that, gosh, I think boys like history more than girls, because I think I'm hearing more from boys that they think their history classes are cool than I'm hearing that from girls. So that's a nice hypothesis to make based on data snooping, which is a good keyword for you to know. So I wrote that, I think boys like history more than girls. Okay, so pause the video and convert that into our special language. Let's see how you did. Here's what I wrote. With respect to liking history, there is a difference between boys and girls. Okay? Now, this isn't the only way you could write this as like a full points answer on a quiz or a test, but it's one way. So I want to break this down just a little bit. The two populations, in this case boys and girls, they are what you're thinking there's a difference between. So notice how I wrote there is a difference between boys and girls. These are the populations. The thing that I think is different comes first. This is respect to liking history. That's what I think is different. Now, I want you to pause the video and turn this into the null hypothesis. Okay, this is super easy. If you have a hypothesis, then all you need to do is change the there is a difference to say there is no difference. Okay? The null hypothesis is just the opposite of the hypothesis, kind of like the anti-hypothesis. Okay, let's take a look at the standard deviation and the normal distribution, and we'll do a little problem regarding that. So the normal distribution just says that the frequency of results is going to be in this bell-shaped curve, and there's some special things about that curve. We have an average. In this case, it relates to the problem. We'll get into that in a minute. But our average is 40,000, right? And so this is our average, and 68% of the data is in this zone. And what is this zone? This zone is one standard deviation away. So each of these dashed lines is one standard deviation. Remember, standard deviation is this Greek letter sigma. So 68% of our data is either going to be 1 sigma, it's going to be between 1 sigma less than 68 and 1 sigma greater than 68. So there's our one standard deviation. And then we also know that 95% of our data is within 2 standard deviations from the mean. So I have another standard deviation going out this way and another standard deviation going out that way. So what that tells you is that the data, like if we're looking at all the people in this situation, which I'll explain in just a sec, 95% of our people are going to be within 2 standard deviations of the mean, which in this case is 40,000, okay? So that's the background with standard deviation. There's several pages in your book that goes over that. I even have a video as well that goes over some of that as well. Okay, so here's a problem that we can answer with this graph and with the idea of standard deviation. I used to work in the mortgage industry, and what that meant I did is I helped arrange home loans for people who wanted to buy maybe their first home. And you'll probably go through that process at some point in your life. Homes are very expensive. Most people don't just have the cash in the bank to just go, here's your money, I'd like that home. They have to put a little money in, but then they have to arrange with the bank to get the rest of the money so that they can buy that home. And then they owe that money to the bank and they make payments on it every month. And that's pretty much how that works. So part of the process, because you might imagine, banks want to make sure that the people they lend money to can actually pay it back. They don't want to give you a big pile of cash and then have you go, I can't pay it back, because then the bank's in trouble and you would be in trouble too. So here's how they figure this out. They have a certain amount of income that you need to make every year in order to qualify for that mortgage. So the situation is this. Of our people that we're looking at, the average income is $40,000 a year. So that's the average income. And on our graph, that's right here at the top of the bell curve, and I marked it at 40,000. Now, in this situation, I'm going to tell you that the standard deviation is $66,000 a year. So 1 sigma, that's this is the sigma value right there. 1 sigma is 6,000. So now I can label it on my graph. 6,000 that way, this makes 46K there, and 1 more sigma that way makes 52K there. So now we have our units on the graph. Same way going backwards, this is 34K, and this would be 28K. Okay? So now we have our units. We know that 95% of the people make between $28,000 and $52,000 a year. Okay, so now we've populated our graph, and now we can answer this question. And here it is. If income must be over $52,000 a year, how many people will qualify for a loan? Like, what is the percentage of the people? Like, if I get 100 people and I want to check them out and see how many of them will qualify for this mortgage, I need to do this analysis, and then I can get a percentage that I can say a certain amount of these 100 people will qualify for a home loan. So let's take a look at how that would work. If income has to be over $52,000, that's the people that are here and that way, okay? So this is $52,000 and more, okay? So now we just need to figure out from our graph here, what percentage of people do make $52,000 or more. And in this case, it's not very many. In real life, it's a bigger number, but I just wanted to set this up this way so that we can do this critical thinking. So here's 95%. That's between 28K and 52K. So all these people don't qualify. You got to make more than 52. This 95% is definitely 52 and less, all the way down to 28K. So what's left? 5%, right? 100 minus 95, there's 5%. So do you think that means that 5% of the people would qualify for a loan? Actually, it's not. Because half of that 5% is down here. This is 2.5%, and that's making less than 28,000. So these people don't qualify. So it's only these people, and that's 2.5%. So this might be like a premium quality loan with an ultra low interest rate, and the reason they're willing to do such a nice thing for you is that your income is really, really strong. So that's how you can answer this type of a question using standard deviation and the normal distribution. Okay, let's do a complicated problem figuring out the expected values. But before we do that, I just want to remind you that with coins and dice, you use theoretical probability to figure out what's expected. So if you flip a coin, theoretical probability says that you should expect to get heads half the time and tails half the time. Okay? But we're not doing that. We're doing this with populations. So I've come up with a hypothetical problem. We're going to figure out the expecteds. So here's my question. Kind of silly, but I'm curious to know if there's a difference between men and women and whether they like yams or don't like yams. Okay? So pretty simple. And I'm giving you 3 numbers, and that's all you need to figure out your expected values. So I'm telling you that there's 40 men in our study, and I'm also telling you that 52 people like yams. And I'm telling you that there's 74 total people. So now we can do a little subtraction and figure out, first off, how many women. That's 74 minus 40. That's going to give us 34 women. And then how many people don't like yams? That's just going to be 74 minus 52, which is going to be 22. Okay? So now we know how many men and women and how many like and how many don't like yams. So the trick for figuring out your expected values is you assume the null hypothesis is true, that there is no difference between men and women and whether or not they like yams. So what that means is that the proportion of liking yams to total is going to be the same as the proportion of women who like yams to the total women. So that's the underlying concept that lets us do the following math. So if those proportions I just mentioned are the same, then the proportion of like yams to total, which is 52 over 74, is going to be the same as the proportion of the women who like yams to the total women. So the way we get that is we use this proportion, that is our proportion, and we multiply it by the total number of women. Had to get my handy-dandy calculator. So I'm just going to do that math. 52 divided by 74 times 34 equals, and that gets me 23.9. So that's my expected value. 23.9 women like yams. Now expecteds, you have decimals, and you should. Now if we asked a bunch of people these questions, we wouldn't have a decimal because you can't have 0.9 of a woman. You'd have 23 or you'd have 24. But expecteds have decimals. Now I can get the rest by subtraction. It's pretty simple. I just subtract 29.3 from 34. 34 minus 29.3. That's going to get me 4.7. That can't be right. Let's try that again. 34 minus 23.9. I know what I did. That's 10.1. Now I can get this number by subtracting 10.1 from 22. And get 11.9. I can get this number by subtracting 11.9 from 40. It's 28.1. And now as a double check, these two numbers should add up to 52. And I think if you look at that, you'll see that they do. So now I have my expected values for if the null hypothesis was true. Now when you do your chi-square, you're going to have your observes in here also, and you're going to use all that data to do your chi-square calculation. Okay, let's do another example and do a complete chi-square calculation. Okay, so I'm simplifying this a little bit. I just wrote yes and no for my questions. This could be like yams, don't like yams. This could be like red, don't like red, whatever your question is. And then instead of telling you populations, I just said one population and two. It could be boys and girls, men and women, freshmen and sophomores, whatever your question is. And then I put numbers in my table. But before we get to that, here's this essential formula. Chi-square is observed minus expected squared over expected. And then I put plus, dot, dot, dot. You're going to get a fraction for every situation. So for coins and dice, it tends to be just 2 fractions. But for populations and a question, it's 4 fractions, 1 for each box in the table. Okay? And so let's take a look at this table. I know the writing might be a little small. You might need to zoom in a bit or make it full screen just so you can see all of that. So what I've got are my totals on the outside, just like we did. And then I figured out my expecteds. Those are the values if the null is true. And then I just made up some observed. So you can see what I did is I decreased the expected by 2 here and increased it by 2 there and did the same thing with these 2. So there's a small difference here, and we'll get a chi-square value that will show us what that is. So pause the video right now and do your chi-square calc. Okay, let's see how you did. Here's my plug-in step. And remember, I want to see that on a test or a quiz, okay? You've got to show me this plug-in step, because if you make a little mistake here, it's going to throw everything off But if it's only a little mistake there, I'm not going to ding you for too many points. Maybe even only a half or a quarter point. But if you don't show me that, and I can't tell where you went wrong, you're going to lose more points. So do your plug-in step. I recommend showing this step so I can evaluate each fraction to see how you did there. Add your decimals up and show your chi-square value. Now, for these decimals, what I did is I rounded it to the hundredths place. So I rounded it to that digit in each case, okay? And I got a chi-square of 1.07. Okay, so that's how you do your chi-square. Now, the last step in this calculation is to look up the probability that the null hypothesis is true. So if you can do that, what I want you to do is pause the video right now, go find that table. You might need to go on the weekly planner or open your book. Find that table and tell me the probability that the null hypothesis is true. Okay, let's see how you did. I get about a 29% probability that the null is true. Now, if this part still confuses you, I have an earlier video that talks just about how to use that table and come up with that result. Okay, so I want you to remember that percentage because we're going to use it in the next little bit here. Okay, so once you've done your chi-square calculation and you've looked up your probability, you need to decide whether or not you can reject your null hypothesis. And this is important because if you can reject the null, then you can make a pretty strong conclusion based on your study. So we'll look at a lot of different probabilities, but let's start with that last one that we did. So what we had was a 29% probability that the null is true. Okay? So that also means that there's a 71% chance that the hypothesis is true. So it seems like our data does support the hypothesis. But the question is that enough to reject the null? 29% chance true. If you said no, you're right. 29% is close to 1 in 3 times that you would do this study and get this result, this lower probability for the null, but nonetheless the null would actually still be true. So you cannot reject the null in this case. You cannot come to a strong conclusion about your hypothesis. So let's go to what can you say? Because you can say something. In this case, I think you can say the hypothesis is more likely true. Okay? Because it's definitely more. 71 to 29, it's like more than 2 times more likely to be true. So you can say more likely. In this case, I wouldn't say most likely. You'd want it to be a little bit higher. Very likely, you're going to need like a 90% chance that the hypothesis is true to say very likely. If you want to say almost certainly true, you're going to want to be like a 96 or a 98% chance that the hypothesis is true to say almost certainly true. So one last thing we talk about conclusion here. Would you call this study inconclusive? Now remember, that's a key word that says, we don't really know. Our results are what they are, but we just really can't say anything strong about that. In this case, I don't think I would say inconclusive because you can say that the hypothesis is more likely true. However, would you bet $1 million on this conclusion? No way. No way. You're nowhere near certain enough. You're just more likely true. So it's not inconclusive, but it's not super conclusive at the same time. So I know this is kind of challenging. We're used to math being like 2 plus 2 is 4 all day long, every day of the week, all for end of time, and that's true. But in statistics, you don't have that level of certainty. It's just not available to you. But let's say you had an 85% chance that the hypothesis is true. Now you're getting into the zone where you might consider rejecting the null hypothesis. In this case, I would think, I might not bet a lot, but I'd say, yeah, I think we can possibly reject the null. If you had a 92% hypothesis true, then I think you can reject the null. Get a feel for this, and just be sure that when you answer that question on a test, and you decide whether or not to reject the null hypothesis, you explain your reasoning. So if you reject the null at 85% hypothesis true, it's not as strong as some people might like, so you want to qualify that answer. You want to say, yeah, I think we can reject the null, but we might not be super confident about that. We're feeling pretty close, but not super confident. If you had this, you could say, we can confidently reject the null hypothesis. Okay, one last word. Make sure that you study effectively. Drill back through the book, back through the activities and the exercises, and focus on the ones that maybe gave you trouble the first time around. Don't do endless chi-square calculations if you have that wired. You've got that done, maybe do one more, but don't feel like you've got to do a million of them. But if you struggle with standard deviation and the normal distribution, I think we did 3 or 4 in class. I handed out a worksheet that had one of those problems on it. You probably want to drill into those and make sure you can answer those correctly. Also, get together with pals and other study buddies. 2 people can often get through material faster and support each other better than one person can. Also, reach out to me for extra help. There's an extra help session the morning of the test. All those good things. So study hard. I look forward to grading your tests. I hope everybody does well. Now that you've watched the video, take a moment to write down some notes or questions or a short summary of the lesson. You can also re-watch portions of the video that you didn't get so well the first time. If you enjoyed the video, please click like. If you'd like to help me grow my YouTube channel, please click subscribe.